Hello guys, welcome back to the channel H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 15 from the course, but make sure you have watched the previous ones before viewing this one. In the last few lectures, we have been discussing quite a lot about the Bohr's atomic model he gave for hydrogen atom. So in this lecture, let us learn about the merits of his model and how he was able to explain the hydrogen spectrum. So the first merit of the Bohr's atomic model is that it was able to explain the stability of the atom. So we have discussed quite a lot about this. So I would be just quickly revising. So the electron, it does not lose energy while it revolves in a particular orbit. It does not jump from orbit to orbit without undergoing change in energy. It cannot lose energy when it is in the first energy level, as there is no lower level available for it to go further down. Right? So I hope this is clear. And thus the gradual loss of energy, this is not possible. Hence the atom is not going to collapse and it is stable. Right? Then he was able to explain the spectral lines of hydrogen also. How he was able to do that? The spectral lines, they are formed when the electron is excited to energy level, and then when it wants to come back to the lower energy level, this is emitting energy. Right? So this energy, it is being emitted in the form of electromagnetic radiation. These electromagnetic radiations, they have discrete frequencies and hence different spectral line series they are formed, and this explained the quantization of energy as well. Right? I hope this is clear. We have spent quite a lot of time discussing all this, and then a large number of lines are formed in the hydrogen spectrum. Well, the hydrogen atom, you can say that this consists of only one electron. So how are we seeing so many spectral lines? It should have been just one spectral line, right? For example, if it is coming from N2 to N1, it is going to be one spectral line. But we are seeing so many spectral lines. Why is it so? Well, it is because a given sample of hydrogen, this consists of a large number of hydrogen atoms. For example, 1 milligram of hydrogen, this is going to consist of 6.02 into 10 power 20 atoms. So these many electrons also, right? So on absorbing energy, these so many electrons of the so many atoms, they are going to absorb different amounts of energy to become excited. And when these excited electrons, they are going to emit energy, they are going to drop randomly to different lower energy levels, and hence we get so many fine spectral lines, right? So this is why, because a large number of hydrogen atoms, so large number of electrons, so large number of lines, right? Now there are certain things which I want you to visualize again in the hydrogen spectrum diagram. Okay, so this was very important, so I've brought it back again. We have to understand the correlation between the Balmer's formula, the Rydberg's equation, and the Bohr's atomic model. Balmer just took some value of n so that the wavelength of all the spectral lines he could see in the visible region, they could be calculated, right? There was no understanding why he was taking some particular value of n. Similarly, in the Rydberg equation, the all series that were formed, he took for the Lyman series n to be 1. For the Balmer series, Balmer had already said that the n1 was 2. For the Bastian series, n1 was 3, and so forth. So Bohr was the one who was able to explain what are these values. Well, n1, n2, n3, these are nothing but the orbits or the energy levels, and you now understand them well. Right? So when the electron, this is excited, and it is then coming back to the lower levels, and if it reaches to the ground state, that is N1, then the energy radiations that are forming, they are falling into the UV region, and we call them as the Lyman series, right? So now similarly the Balmer series when N is 2, and Paschen series when N is 3, and so on. Apart from this, there are many more interesting and important things that you should understand. The energy is increasing from N1 to N infinity. I hope this is clear. We have discussed this. So when an electron, this is making a transit from N2 to N1. This is going to be the least energy transition. When you are seeing N3 to N1, this is a bigger line. So N3, N4 to N1, another bigger line. So this is more energy transition, right? So this is the lowest energy transition. So this means that this is going to be the lowest frequency transition also. And correspondingly, this is going to be the longest wavelength also. So this line of the Lyman series, you can call this as the longest wavelength line, right? Similarly, for all the series, this smallest line which we can see on the diagram is actually the longest wavelength line, right? Can you remember that? This is very important. The first line of the series, the longest wavelength line, and we call this as the alpha line. This is the alpha line. The next is beta, then gamma, then delta. Similarly here, alpha, beta, then gamma, delta, and so on. Again for the Paschen and rest of the series also. So the first line, that is the alpha line. This is the longest wavelength line. And what will be the shortest wavelength line then? The line which is coming from infinity to the lowest level, right? For the Lyman series, N infinity to N1, this is the shortest wavelength line. And what do we call this line as? We call this as the series limit line or the limiting line. Okay, so here the series is limited. We are ending it. This is the first line, this is the limiting line. Okay, so the longest wavelength, the shortest wavelength. Fine. I hope this is important. You remember, because this is very important. Sometimes in the questions only it is said that the limiting line or the series limiting line is this much and things like that. So you should understand these terms. The first limiting, the first line, the limiting line, the longest wavelength line, the shortest wavelength line, right? Now, the energy difference between two energy levels, we know what is the energy of one level. En is minus RH into Z square by N square. So E1 would be what? Minus RH into Z square by N1 square. And E2 would be minus RH into Z square by N2 square. And if we take the difference of them, that is E2 minus E1. So what would you get? This delta E is energy that is being emitted or absorbed. This has a particular frequency, so it is h nu. So h nu is minus RH into 1 by N2 square minus 1 by N1 square into Z square, right? Or h nu we can write as hc by lambda, and if we want to convert this negative into the positive, we just interchange the positions over here. It becomes 1 by N1 square minus 1 by N2 square. And if we have 1 by lambda, so 1 by lambda is going to be also called as wave number. So this is going to be what? RH divided by HC, right? And if RH by HC, you calculate the value, you are going to get this as 1096677 centimeter inverse, right? So this is the value which Balmer took in his formula and Rydberg in his equation. So this is how we have got this value, right? So I hope you can understand how Bohr's atomic model, this can be correlated to the hydrogen spectrum, the Balmer formula, and the Rydberg equation, right? This is very important, so please do understand this well. Now there are certain terms which also I want you to remember here. They are very important. Again, They are used in your numericals also, and also in the further courses we will be using these terms. So what is excitation potential? You already know what is ground state, what is excited state. So the energy required to excite an electron from the ground state to any excited state, this is called as the excitation potential, and this is going to have a positive value. For example, the first excitation potential for hydrogen atom is going to be E2 minus E1. Then the second one is E3 minus E1. The third is E4 minus E1. Right? And then we have the ionization energy. What is ionization energy is going to be when we are going to remove an electron from the ground state and take it up to n infinity. Okay, so we are removing the electron completely from the electrostatic forces of attraction of the nucleus. We are just removing the electron from the atom. That energy that we have to supply, that is the ionization energy. So how do we define it? It is the energy required to remove an electron from the outermost orbit of a gaseous atom in the ground state. This is called as the ionization energy, and its value is also going to be positive. For example, the hydrogen atom, this has one electron, so n is going to be 1 for the ground state. And if we want to take this electron to n infinity, the energy of n infinity is 0 electron volt, and energy of the first orbit is how much? Minus 13.6 electron volts. So the ionization energy is going to be 13.6 electron volts, right? So I hope it is clear. And then the next term we have is separation energy, and this is the energy required to separate an electron from any excited state of an atom. And for example, the first separation energy, that is the energy required to remove electron from the first excited state. In case of hydrogen, this first separation energy is going to be plus 3.4 electron volt, right? Now see this diagram also. Another important thing that we have to discuss, that when an electron is de-exciting, it can de-excite in many number of ways. Right? For example, we have an electron which is de-exciting from N4 to N1 in this diagram. So how many number of spectral lines can be possible for this transition? That is what you have to tell as an answer. Okay, so how will you do that? When an electron is in N4, it can directly come to N1. It can come first to 3 and then from 3 to 1 direct jump. Then either it can do that, it jumps from N4 to N2 and then it comes from 2 to 1, or it can come first to 3, then to 2 and then to 1. So there is a number of ways in which it can do its transition. So how many spectral lines are possible? Let us see, count them. 1, 2, 3, 4, 5. This one is common to this, so we will not count this. Then we have 6, and again this one is common. So for N4 to N1, 6 lines are possible, right? So there can be, for each transition, for example, from N5 to N1, you may have to calculate the number of spectral lines. So there is a formula. We do not have to draw every time this diagram and then count the number of lines. We have a formula which we will directly and tell how many spectral lines are possible. So the number of photons emitted or the number of spectral lines produced when the electron, it jumps from the nth shell to the ground state due to all possible lines. The formula we have for ground state, remember this formula is only for ground state, and this formula is n into n minus 1 divided by 2, where n is the outermost shell, right? For example, in the diagram we saw n was 4, so 4 into 3 divided by 2, 12 by 2, we get this as 6, and you counted that we had 6 spectral lines possible, right? So if it is not coming to the ground state, to any other level, then what the formula we use is that the maximum number of lines that can be emitted when the electron de-excites from N2 to N1, where N2 is greater than N1, is that N2 minus N1 plus 1 multiplied by N2 minus N1 divided by 2. And this N2 minus N1 you can write as delta N, but you should remember that what is delta N then? Delta N is N2 minus N1 and delta N multiplied by delta N1 plus 2. And if you see, put the values, even for the ground state, when you put that as 1, you will get the same formula. Okay, so this formula is coming actually from this formula only. The above two formulas, they are for a sample of hydrogen atoms. Okay, so when there are many atoms, there are many electrons, so there are many spectral lines. But if we have a single isolated atom making a transition from the nth stage to the ground state, the maximum number of lines possible is n minus 1. Okay, so please do remember, questions do come on this also. So now we have the have and it section for you here, which is consisting of the graphical representations of a few variables. You have in front of you many graphs. First is between the radii of the orbit and the n and z values. So r was directly proportional to n square by z, right? So if r is directly proportional to n square, the line formed is a straight line, and r is proportional to 1 by z. So again we have a straight line. In between, when we draw a graph for r and n, this is the type of graph you will get, and when we are taking it for r and z, this is the type of graph you will get, right? Similarly, the velocity, that is proportional to z by n. So we have z and v graph to be a straight line and v and 1 by n to be a straight line. Between that v and n, this is a graph like this. So these are just to tell you, do not get worried when you see certain graphs being formed. You can even try putting various values and find such graphs. Okay, so this is how these graphs are going to look like, and they are sometimes asked in the question, so you do not get worried of them. That is why we have put all together for you. So similarly, the graph between energy n and z is also drawn for you. So energy, that is proportional to z square by n square, right? So with n square and z square you can see, but these are negative energies, so they are in the fourth quadrant, you can see, and that is the other part with n square, z, 1 by n and n. You can try drawing them, all of them. You will find them interesting also, and that would help you remember the type of graphs that are being formed, right? Now another one thing that is interesting is that in the spectral lines of hydrogen atom, the intensity of line, this decreases with increase in the value of N2. So you can remember this also. And now we have another name for another series of the spectral lines when the electron is jumping from the outer shell to the sixth shell of the hydrogen atom. So this is called as the Humphrey series, okay, from outer shell to sixth shell. And the lines of the Humphrey series, this also lie in the infrared region, and the Balmer formula or the Rydberg equation, you can say, is going to be 1 by lambda equal to nu bar into is equal to r into 1 by 6 square minus 1 by n2 square centimeter inverse, where n2 is going to be 789 square, so forth, right? So I hope all this is clear and interesting for you. So this would be all for this lecture. A very important lecture, a very important topic is about to finish. So please do revise all the lectures on the BOHR'S model before we put up the next lecture, because in that we are going to discuss about the numericals on the BOHR'S model, which you will be able to understand well if you have understood the whole topic well, and you know all the formulas, right? So please do learn them before seeing this lecture on the numericals on Bohr's model. Till now, if you have any doubt, please do feel free to mail us at h2ochemistry@gmail.com. And if you've liked the lecture, one request, please do click on the like link, and also do subscribe to our channel H2O and click on the bell icon so that you get a notification as and when we put up a new lecture for you, a new course for you. That would be all. Have a nice day. Enjoy yourself.